All right, welcome to this explainer. We're going to take some pretty dense engineering statics and flip them into a dynamic, step-by-step study session. If you're an undergrad engineering student getting ready to tackle your exams, well, you are in the perfect spot. Today, we aren't just reading through dry textbook theories, we're actually building out your engineer's toolkit. We're getting right into the exact math that keeps bridges standing and keeps heavy-duty cranes lifting. So let's just dive right in. Here's our game plan for today. 1. Statics basics. 2. Real-world forces. 3. Parallelogram law. 4. Problem-solving steps. And finally, 5. Cartesian vector notation.
Section 1. Statics basics, scalars versus vectors.
Okay, let's kick things off with a quick inventory check of our absolute most basic engineering tools. Take a split second to test your memory here. Which one of the following is a scalar quantity? Are we looking at A, force, B, position, C, mass, or D, velocity? Go ahead and lock in your answer.
Well, if you went with mass, you are spot on. A scalar, like mass, volume, or length, is straightforward. It literally only has a magnitude. You can just add them together using basic arithmetic, right? 5 kilograms plus 5 kilograms is 10 kilograms. Easy. But vectors, like force and velocity, are kind of a whole different beast. They demand both a magnitude and a very specific direction. Because of that directionality, simple arithmetic just completely goes out of the window, and we have to rely on geometric rules to actually combine them.
Section 2. Identifying real-world force systems. Now, let's step out of the abstract and see what happens when these vectors actually impact the physical world. Think about a massive, heavy-duty crane hook being pulled by 3 separate chains, or a giant industrial barrel suspended midair by a 2-chain sling. If we mentally animate these operations right now, imagine the intense downward gravitational pull of that load. To maintain static equilibrium, the chains absolutely have to pull back up and outward. That immense tension running through those solid metal links, that represents our force vectors in action. As engineers, our entire job is to calculate these vector interactions so we can definitively say whether these structures will hold, bend, or, catastrophically break.
And to prevent that kind of catastrophic failure, we have to calculate the net force. The net force isn't just lazily adding some numbers together. It's the complete geometric combination of all those independent chain pulls acting on a single particle, like the solid steel ring of that crane hook. It represents the ultimate net effect. Because if that combined net vector exceeds the material's yield limit, the hook snaps.
Section 3. The parallelogram law, unlocked.
So, how exactly do we combine these directional forces together? Time for another quick knowledge check. For vector addition, you have to use which law? Is it A, Newton's second, B, arithmetic, C, Pascal's, or D, the parallelogram law? Think back to the specific geometric rule we have to rely on here.
Yep, the answer is the parallelogram law. If we want to resolve a single force vector into components along 2 separate intersecting axes, let's call them U and V, we essentially just build a parallelogram. Imagine literally drawing a line straight from the head of your main force vector, running perfectly parallel to the U-axis until it hits the V-axis. Then, you just do the exact same thing starting from the V-axis. Those components form the adjacent sides of our shape, and the original force acts right down the middle as the diagonal. It's just a beautifully visual way to break down a really complex pull into 2 totally manageable directions.
Section 4. Step-by-step problem solving.
Okay, let's transition into the exact tactical system you're going to use to completely defeat these tricky coplanar force problems on your exams. Consider this your ultimate survival guide. It breaks the resolution of force vectors down into a foolproof 6-step sequence. Trust me, when you are staring at a blank piece of paper during a high-stakes midterm, you do not want to rely on sudden inspiration, you want to rely on a cold, repeatable process. So let's translate that process into our core game plan. First, identify your knowns and unknowns. Literally ask yourself, what do I have and what am I looking for? Second, draw the free body diagram and label everything. Seriously, never skip this step. Third, sketch out that parallelogram law so you visually understand exactly how the forces are interacting. And finally, step 4, let trigonometry do the heavy lifting. You're going to use the law of sines and the law of cosines to calculate your exact final values.
Let's actually see that trigonometry in action. By plugging your newly mapped vectors straight into the law of cosines, taking the square root of the sum of the squared forces minus 2 times the forces times the cosine of the angle, you get to watch all that abstract geometry instantly lock into a concrete resultant force. In this specific example, the math spits out a super clean resultant force of 213 newtons. Then, by applying the law of sines right on its heels, we find an exact angle of 39.8 degrees. Guys, this right here is the absolute gold standard for formatting your exam answers.
Section 5. Cartesian vector notation applied.
To wrap things up, let's look at an alternative mathematical approach. See, while sketching out parallelograms is awesome for visualizing two forces, it gets unbelievably messy the second you have three or more forces pulling on a single point. And that is exactly where Cartesian vector notation saves the day. Instead of drawing complex shapes, we just mathematically resolve every force into strict horizontal and vertical components. We grab the horizontal component by multiplying the force magnitude by the ratio of the horizontal leg of a slope triangle. We label the horizontal with an I unit vector and the vertical with a J unit vector. It literally turns messy geometry into pure scalable algebra.
Let's ground this with a concrete example. Imagine three entirely different forces acting concurrently on a metal bracket. Instead of trying to draw this massive, confusing web of overlapping parallelograms, we just break F1, F2, and F3 into their individual horizontal I and vertical J components, going line by line. We are essentially figuring out exactly how much each specific force is pulling left to right and exactly how much it's pulling up and down.
And honestly, here is the real magic of Cartesian vector notation. Once absolutely everything is sorted into that I and J format, you just sum up all the I components together and all the J components together. The total chaos of three diagonal intersecting forces just neatly collapses mathematically into a single, clean resultant force equation. Our net horizontal pull comes out to 972.7 newtons, and our net vertical pull is 102.7 newtons. From there, tracking down the final magnitude is literally just running the basic Pythagorean theorem.
Well, we have definitely covered a lot of ground today. Everything from identifying basic scalars to breaking down complex concurrent forces with advanced trigonometry. But I want to leave you with this final thought as you head back to your study guides. Now that you have this mathematical toolkit to calculate exactly how much net force is acting on something like that crane hook we visualized earlier, the real engineering challenge begins. Because it isn't just about finding the right number on a page. It's about asking, how are you going to use this data to design a material that actually prevents the system from snapping in the real world? That right there is the true essence of engineering statics. Thanks for hanging out with me for this explainer. Keep practicing those free body diagrams, and I'll catch you in the next one.